there has to be a minimum diameter, discharge diameter, that should be there for the mass flow of the particles. So hope you all revised and at least gone through the PowerPoint slides what I'm explaining, and hope you all understanding what I'm trying to teach. Please, it is a long subject to go into how particles behave, what mechanics and everything. As I said initially, if I have to teach only this part, it takes whole semester. But I have only, it is a only small topic in our syllabus. So I'm just presenting whatever is necessary, the details. Okay. So hope you're able to follow. So today I will conclude this silo design, and I will give the detailed design procedure and all those things. Before I move on, is anyone have any questions? Kindly ask me. Otherwise, we'll start with today's discussion. Hope you're able to understand, right? Are you able to follow my lectures?
Yes, sir.
Okay. So thank you. So it seems no questions. We'll continue the last part of storage of bulk solids.
Sir, I have one question.
Yes, please.
Sir, so sigma c is the property of bulk, or like it depends on sigma 1?
Which one? Sigma?
C.
Sigma C. Okay. Sigma C is a bulk property. When you have a more number of particles together, when there is a consolidation stress, when you apply some stress from the top, how they interact with each other, that is come from the sigma C.
So like initially, if I applied a certain like stress in order to uh, move the particles closer and together to form a
Yes.
bulk. So sir, sigma c depend on that initial stress that I have applied.
Correct. That depends upon the initial stress and also depends upon the internal friction, that is interaction between the particles also, and also the interaction between particles and wall also.
Okay, sir, got that. Thank you.
Yeah. So rightly, as you rightly asked, I brought the same thing what we discussed in the last class. Thank you to the student who asked the question. So here we discussed in the last class sigma C, unconfined yield stress. They depend upon the compacting stress, the initial stress, what we are applying. So you can see here very clearly, if you have initial compacts as this much, and you will have this much of sigma C. This is sigma C and this is sigma 1. Consolidation stress or compact stress. So we discussed last class that we put a powder in an enclosed area. We apply some initial stress, that is called compacting stress or consolidation stress. After that, we remove the enclosed area like cylinder. Then we apply pressure, keep increasing until we see there is some fracture. Fracture means what? The flowability of the particles started taking place, right? Let me give an example. Let's say there is a cohesive. Cohesive means all particles are interacting and making sure that all particles are sticking to each other. Let's say we have a certain amount of stress in the horizontal and we're applying some vertical stress. Vertical stress, right? So keep this constant. Let's keep this horizontal stress constant and keep increasing. Let's say keep increasing this one. Keep increasing this one. We are keep increasing this one. So what will happen at some point of time? There'll be, if you keep bringing load, there'll be fracture in this direction. Okay. If you apply further load, what will happen? Can anyone guess after fracture? If keeping this is constant, if you apply this one further, what will happen? Can anyone suggest me? So we have a cohesive solid. Yes, please.
That flowing along that break line.
Yes, that is true. So this will move in this direction. This will flow in this direction. So this is the amount of the critical stress is the minimum stress which we need to apply for the flow of the particles, the flow of solids to take place. So I'm glad that you all understood that concept. So this is the flow function. Varying the initial compact stress, we will have the different sigma c values and relation between sigma c versus sigma 1, that is consolidation or compact stress, versus unconfined yield stress is the flow function. This also we have seen. Based on that, we have defined the FFC mobility factor.
Sir, I am asking that you taught about lateral stress. There's lambda is equal to sigma h upon sigma v. So on generating sigma v, there also should sigma h come into role. And here you said that sigma h we are keeping constant. So
I just give an example. You can vary sigma h. You can vary sigma v. Sigma h come from the sigma v. From there we get the k.
Yes.
Here I just to make you understand the small principle that how the flowability takes place beyond the critical stress, I have explained. This is only figurative. Don't take it as active. Actual phenomenon.
Okay. Sir.
Okay.
Yes.
Yeah. Thank you. So sigma h, sigma v, that is relation is come from the lambda or k. That is the actual phenomena for a two-dimensional particle. This example what I given you just to make you understand. Okay, kindly don't get confused. This is the probability factor we have discussed in the previous class. Just to show, this is the sigma 1 by sigma c, and based on this, if it is less than 1, definitely no flow is taking place. So it has to be higher than 1 for the flow of particles to take place. Ideally we wanted greater than 10, but very unlikely that we will have this. Very few particles will have this, like quicksand. There is no cohesive force. So quicksand will give this behavior, but most of the solids will fall in this category. Most of the solids will fall in this category, 2 to 4 or 1 to 4. So we have unconfined yield stress. We have unconfined yield stress, and we have the compacting stress, sigma c and sigma 1. Right? Let's say this is the flowability flow function. This is the flow function, right? For a given silo, it will be having certain conditions, right? We have taken this red line what I've highlighted for very general flow function. This is the very general flow function. The red line what I'm showing here is very general flow function, right? For a given silo, the particles will be subjected to certain compacting stress. Will be subject to certain compacting stress. And based on the given conditions of the silo, we wanted to find out the critical conditions. For a given silo, based on the existing conditions of that silo, we wanted to find out the critical unconfined yield stress value. Okay, that will come from you take the graph between sigma c versus sigma 1, sigma c versus sigma 1. Since we have this function sigma c is 1 over ff versus sigma 1. If I take a line from origin, with a slope of 1 over ffc, okay, ff, I just put ff, but this is ffc, 1 over ffc. This will touch this flow function at certain line, and that will be the critical value. So that stress developed in silo, if stress developed in silo should be greater than this critical critical unconfined yield stress, then only flow will take place. If it is less than this, no flow is taking place. This is the first important condition we need to check. From the there is called Conical Shear Tester. From the tester we can get this plot sigma c versus sigma 1. We get a red line like this. I showed A, B, C. A is for one type, B is another type, and C is another type, right? I'm just giving an example of B here. So once you have a profile of B, flow function of a B, we wanted to find out the critical value of a given Hooper. Given Hooper, how do you find out? Just we have to draw a line from origin 0, 0 with a slope of 1 over f of. Why this is slope? Because sigma c equal to 1 over f of c into sigma 1. So if with that slope, we draw a line wherever it touches this curve, and that will be the critical value. So based on the sigma critical, sigma c is different from sigma critical. Okay, this is sigma c. Sigma critical is this value. If this critical value is higher than the actual stress developed in the silo, then definitely no flow takes place. If actual stress developed is higher than critical flow, then only flow takes place. So once we know critical flow, whether simply gravity is sufficient or we need to give any external load can be understood. Whether we need to give any external load or simple gravity is sufficient, we can determine from this condition. Let's say actual stress developed is less than sigma critical with only gravity. Let's say we have only silo with all the particles are subjected to only the gravitational force. Then if let's say the actual stress developed is less than critical, then no flow takes place. But if we wanted flow to take place, what we have to do? We have to apply some external load. We have to apply external load to increase the actual stress developed in the silo for the flow to take place. Students, guys, do you understood what I'm trying to explain here? For a given silo, we are trying to find out the critical conditions from the flow function. Okay, so hope you all understood. If anyone doubt here not understood, kindly let me know. I can explain one more time. This is important step.
Sir, I haven't understood properly.
Okay, should I explain once again?
Yes, sir, please.
Okay, so do you understood this one?
Yes, sir.
Right, thank you. So we have a flow function for a given material. From a tester, from uniaxial compression tester, we got a flow function, right? This is for all compacting stress conditions. For various types of compacting stress conditions, we got the unconfined yield stress value. Now we have a silo where we have stored this powder. For this silo, we wanted to find out what is the critical sigma c. We wanted to find out the critical sigma c. Critical sigma c instead of c critical, just they write sigma critical. How do you find out sigma critical? If I know FFC value, later I will explain you how to estimate this FFC value. Sigma c equal to 1 over FFC into sigma 1. So this is the line equation, and starting from origin is simply y equal to mx. We'll draw a line with the straight line having the slope of 1 over FFC. This FFC is measured for the silo conditions. This powder is subjected to certain sigma 1. And to find out exactly that sigma 1, or to find out the critical sigma 1, it is hardly difficult to find out exact sigma 1. So rather it will be more easy to find out FFC value. So from that FFC value, if you know the FFC value, we get the slope of the FFC value. 1 over FFC is the slope. We'll touch this line, and this will be the sigma critical. Why we are doing this? Because actual sigma 1 is difficult to predict. Because this is vary from the distance to distance. Rather, FFC value is easy to figure it out. We have many empirical formulas are available. That's why we are following this procedure. That's why we are following this procedure. Do you understood now, the student who asked the question?
Yes, sir. Yes, sir.
Hello, do you understood the one who asked the
Yes,
question?
sir.
Actually,
Yes,
I
sir.
cannot see names and all because I can only see slides, either that or this. So that's why I don't know the names. That way, we'll find out the critical unconfined yield stress for a given silo conditions. Now, once we know this critical conditions, in the last class I've explained that there has to be certain minimum outlet diameter for minimizing or eliminating the arc formation. So there's a huge derivation. I really don't want to get into those details, but please take it this formula. Minimum outlet diameter. This is the conical hooper. This is the conical hooper, and this is the diameter of the outlet. This is the diameter of the outlet. So this is the B. This is the B. The B equal to H of theta. H of theta into this critical unconfined yield stress by bulk density. This is bulk density. Bulk density. Into G. So here we have a unknown parameter here because previous slide we have seen how to calculate sigma critical, and bulk density we can find out from the powder properties, and we have the G value. H of theta, you can use this formula or you can use this graph. We have two types of hoopers. One is conical hooper, another one is wedge-shaped hooper. I will show you in the later slides what is wedge-shaped hooper. Right now we know we are familiar with conical hooper. Okay, so we have two, theta C and theta P, right? Theta C is for the conical hooper angle. So this is the theta C. This is the theta C angle of this hooper. Theta C means angle of the hooper for a angle of a conical hooper. Theta P is angle of a wedge-shaped hooper. Okay, don't get confused. Theta C is for the angle of conical hooper. Wedge-shaped hooper is theta P. Okay, wedge-shaped means just like rectangle. We have a rectangular shaped hooper. Here we have a hooper like this. So this is the wedge-shaped hooper. Sorry, my annotations are not good. Hope you are understanding the 3D picture I have drawn here. So this is the angle for a rectangular shape or a wedge shape is theta P. And this is theta C. I didn't draw a straight line, but hope you are understanding. This is theta C. So once we know the hooper angle, we can easily find out H of theta and critical unconfined yield stress. From that, we know the minimum outlet dimension is required. That is, minimum outlet diameter is required. If the diameter is lower than B, then definitely this arch formation will take place, which obstructs the flow of particles. Okay. Then, so in the previous case, we have a different compact stress. When you have a different compact stress, we have different unconfined yield stress because of the compacting nature, because of the interaction between the particles. Which property that explains that interaction property? One is previously we have also seen the different types of forces, adhesion forces. Another important property is angle of internal friction. Angle of internal friction, which talks about the resistance between the particles to flow. Resistance between the particles to flow. What just simple concept? How do you measure the angle of internal friction? What is the internal friction? Let's say this is a rough surface. Let's say this is a rough surface or a simple soil, like we have a flat ground and which contains we have a soil. Now I have taken a brick. I have taken a brick. Now I have taken a brick. I have applied some load from the top. I have applied some load from the top. Then I am trying to push the brick with some certain shear force. I am trying to push the brick with certain shear force, right? Let's see if the surface is very smooth. If the surface is very smooth, very extremely smooth, extremely smooth. That is one type of surface. Another surface we have a rough surface. Not necessarily in the way you can see, but let's say very fine rough surface. Will the brick move at same speed for the both conditions or differ? Will the brick move at the same speed or will it differ? Can anyone answer? It will differ. Why is that it differs?
Due to
So
friction.
because of friction forces.
Yes,
forces
due to the
upon-
frictional forces. Exactly. Thank you, students. Because of the interaction between the surface and the brick, there will be frictional forces. If the friction is higher, there will be resistance from the opposite direction comes. The resistance offered by the surface takes place. That is because of the internal friction between the whatever brick and the surface we are taking. So I will erase it. So the shear force is proportional to the load which we are acting, and the proportionality equation will be Fs equal to internal friction into Fn, and if we divide it by area, both sides, we get shear force by area shear stress, normal force by area stress. This is the normal stress. So the shear force, the shear stress is proportional to the normal stress and is equal to the viscosity. For fluids in fluid mechanics, we might have seen similar principle, but will be slightly different. There we get the velocity gradient, and shear stress is proportional to velocity gradient, and that will become the viscosity there. And here we have the frictional coefficient. Now we just taken the same forces, normal forces, shear force, and we know if you have an at equilibrium condition, some of the forces equal 0, whether in cyclic or clockwise or anti-clockwise direction. So obviously this will be the clockwise force. Then this will be the angle. Then we can also define the friction angle. Tan theta equal to Fs by Fn. Then we have the divided by area gives the shear stress versus the normal stress, and shear stress is equal to the normal stress into tan theta. So we can express relation between the frictional coefficient. We can also express based on the friction angle. So often the solids, the internal friction, angle of internal friction is more usually used than the frictional coefficients. So this is the Janicki shear tester, which is used to measure this frictional and angle of internal friction. And if we use the material, whatever used for the construction of silo, we can also get the internal friction between the solid and the fluid. So here, two things I wanted to highlight, just to show how do we estimate internal friction between the particles and internal friction between the particles and solid. I think the video representation will make you understand easily. That's why I just selected this video. Sorry, my computer is a bit slow. So what happens? Terrible. Okay. Maybe, yeah, it's taking some time. So let me explain. So this is the, if you want to find out the internal friction between powder, they will take a small cylinder and they will fill the powder. They will fill the powder. They will take another cylinder and that also they will fill the powder. Due to cohesion, the powder will stick. The powder will stick. We can slightly compact. We can slightly compact so that the particles will not flow out. We can compact such that, see, we just take a cylinder like this and just we fill the powder. We just fill the powder. Then we apply small compaction. We apply small compaction so that it will just stick. So that it will just stick to the surface. I would like to show both. Yeah. Okay. Take some time, so I can explain. So we have two flat surfaces. We apply some cohesive force so that it will just stick. So we have two discs. Then we try to shear one over other. We try to move one over other. We try to shear one over other. Then what we get is angle of internal friction between the solids. Instead of two particles filled disc, instead of shearing, what they will do, they will fill the cup with the powder. Then whatever silo material it is there, they will try to shear with that material. They will try to shear with that. This is the solid material. This is the solid material. They will try to shear it. So this will give the angle of internal friction between the silo material and the powder, and this will give the internal friction between the powder and powder. So this is the Conical shear tester, right? We have a cup. This is the enclosed surface, and here we have we are filling the powder. Here we have filling the powder. Here I have given the example of to measure the internal friction between the powder and the silo construction material. So they will just lock. They will put a bracket. They will lock it, and some normal force is applied. And by just tightening the screw, we will apply some shear force in this direction. We will apply some shear force in this direction. We can easily measure the moment of this one. From that, we can easily calculate the angle of internal friction between these powders and the solid surface. Sorry, I'm going very quick because I wanted to finish up this topic today, but I'm sure you all trying to get an idea, right? I got. What's that? Sorry. Yeah. So here you all can see this is just simple simulation. We have particles, and then we made it smooth. Then this is the surface. This is silo material. No, sorry. This is top one, and this is the bottom one, and we're trying to move top cup over the bottom cup, and you can see how that interaction between the particles will takes place. That interaction determines the angle of internal friction. So we have top cup and we have the bottom cup. Then we are filling the solids completely. Then we scrap it out. We scrap out the top surface. See, this is the one cup. This is the second cup, and we're trying to move the top cup over the bottom cup. As it moves, you can see the interaction between the solid particles are taking place. That interaction is basically the resistance created by the internal particles, and that will relates to the internal friction between the particles. So there is another nice video. I think I forgot to. I will show you probably end of this class how also they compact two cups and they measure the internal friction.
So,
Yes, please.
the top plate,
Yeah.
that is silo material.
No, the one which is moving, right? That is just to move the bottom one. here you see, this is not the 1 second. You mean this one, the top one, which is having the like this?
Yes, sir.
So that is not the silo material. Okay, that is just to move this cup, the top cup. This is the one cup. This is another cup. Are you able to see my mouse cursor?
Yes, sir.
Cursor. So where this is the bottom plate, this is the top plate. Okay. So to move this top plate, only this one. This is only simulation. This is not the actual one. Okay. This is simulated result. This is not the actual cup. I have shown the simulated one to see the how the particles moving. In actual cup measurement, you will not be able to see the movement of the particles. Do you understood?
Yes, sir.
Hello.
Yes, sir. I got it.
Okay. I will show you another video where they actually use the silo material to measure it. Okay. Actually, I forgot to copy the link, but I will show you. Right. So this way we'll measure the angle of internal friction, and this is the basic fundamental concepts between this one.
Sir,
Yes, please.
sir, can you go to last slide?
Yeah.
Sir, one more.
One more. Yes.
Sir, is there here tan theta is equal to mu?
Yes. Yes. Correct. Tan theta equal to mu. That is correct.
Okay.
Tan inverse mu is theta. Okay.
Yes.
So here, now previously I have just shown tau equal to frictional coefficient into normal stress. But now this is certain fluids also behave this way. Sorry, certain fluids will behave this way. Certain fluids will behave this way. People have observed that the tau is proportional to sigma, just like Newtonian fluid, and non-Newtonian fluid. Certain powders will behave this way, and certain powders will behave this way. Which powders will behave this way? The powders which doesn't have any cohesion. There is no forces. What kind of forces? Which I explained in the previous class. What is that name? Adhesion forces. If there is no adhesion forces, then there is no cohesion between the particles. Then the shear stress is proportional to the normal stress. It is exactly like a Newtonian fluid in case of fluid mechanics. Okay. Example for the cohesion is quicksand, and a grains without any moisture, like corn cobs, those things without any moisture also behaves like a no cohesive material. But most of the powders, crushed powders, will have cohesion exist. There is some adhesion forces. They behave like tau is instead of proportional to the sigma. There must be some minimum cohesive stress is required before the flow to takes place. Before the flow to takes place, there must be some minimum amount of cohesive forces has to be taking place. That is also internally related to the sigma critical unconfined yield strength value. So the behavior between shear stress versus normal stress will be the C, the cohesive stress, plus, although it will sometimes looks like slightly curved, but often they approximate it to be straight line. Often they approximate it to straight line because the deviation is very minimal. In case of fluid mechanics, we have three different types of fluids, dilatants, and three different types of non-dilutant fluids, Bingham plastics. But here we have only two types, right? So for cohesive edges, then we have shear stress equal to cohesive stress plus normal stress into tan theta. If there is no cohesion, this is the formula. Since most of the particles is when there is cohesion, if the cohesion exists, then we have to find out whenever there is a cohesion, there will be two types of stresses. One is maximum and the one is minimum stresses. There are two types of principal stresses. Principal stresses. Principal stresses. One is maximum, another one is minimum. Max and minimum. We might give a figurative way. Maximum goes in vertical and minimum can be horizontal for a two-dimensional plate. That maximum versus minimum stress equal to 1 plus sine theta by 1 minus sine theta. Actually, this come from the Maher's stress circle or Maher's circle. Have you heard about this one in the strength of materials course? Maher circle or Maher stress circle. Students, in the last
No,
year,
sir.
have you learned? No, okay. So I will, if time permits today, I will explain this. Otherwise, I'll explain quickly in the next class. Okay. How do you get this principal stresses from this Maher's circle? So we have maximum versus minimum stress ratio equal to 1 over 1 plus sine theta by 1 minus sine theta, and these can be measured from the Janicki shear tester. We can measure this from the Janicki shear tester, which is shown in the previous slides. Okay, so we have sine theta by 1 over sine theta. We know this value. Obviously, we can calculate sine theta. So theta value, the theta is effective angle of internal friction. This is commonly used. Similar manner, angle of internal friction between powder and Hooper were also determined, which I explained before. So today so far we have learned three things. One is that critical unconfined yield stress, angle of internal friction between the powder and the wall or the silo construction material. We have learned three concepts. Hope you all understood up to this point. If you have any doubts, kindly ask me now. Okay, thank you. No questions. So,
Sir,
yes, please.
is that C is equal to sigma critical,
Which
or
one?
is there any relation?
This is
Sir,
not
here.
sigma critical. No, this is not the what to say. It won't be sigma critical because we are not doing any compaction. We are not trying to do any compaction here. Okay, but this is related to sigma C. The C is not exactly sigma C. Okay, it is related because that is depends on the various compaction levels we have the sigma C.
Okay, sir.
So here we just talk about the free flow particles. Okay, just particles are just placed without any compaction. That is where we are talking about this. In case of sigma C, we are doing certain amount of compaction. So to attain mass flow or the free easily flowing conditions in a silo, so far we can understand that the Hooper angle is critical because that determines and also that depends on the angle of internal friction between the particles and angle of internal friction between the material and this outlet diameter. If you want to attain free flow, these two has to be maintained certain numbers. Then only you will get the free flow condition. There are basically 4 types of Hoopers, but primarily two types, but that is replicated. That is just replicated here. So we have the conical Hooper. Another one is rectangular cross section with the wedge-shaped Hooper. Then we have the symmetric Hoopers. Like half of this one we have taken. We have only taken the half of the cross section. C is D is this one, C is this one. But people found out that we will never be able to attain proper flow conditions in these cases. So people are not using. Although initially these are the types used, but people are not using this. In the modern days, these are the only 2 types used. The only 2 types used. So whatever procedure I'm going to explain this one is exactly same for this one. So since the Hooper is the critical. Hooper angle is critical. How do we estimate the conical Hooper angle? How do we estimate this conical Hooper angle theta c? How do we estimate the conical Hooper angle? Okay. So the vertical stress acts in the Hooper. The vertical stress acts in the Hooper. I have a derivation at the end to make it simple for the. I have the derivation which I have in the end of this class will be with some assumptions, with certain assumptions. But now the actual vertical stress acts in the Hooper very complicated. So Janicki has derived instead of making a derivation. He has brought out an empirical relationship. He has derived an empirical relationship from the various experimental results. The vertical stress acts in the conical Hooper is a function of radius, bulk stress. Sorry, what is this? Bulk density. Then we have the angle of internal friction. All those things, and this is very complicated. So he has derived the derivation. Again, I don't want to get into all those derivations because we need to explain a lot of other fundamental concepts. But for us, most important thing is the empirical relationship. What he has published or what he has given in the books is this one. This phi of x. The phi of x is angle of wall friction. Angle of wall friction. Phi of V is the angle of internal friction. Angle of internal friction. So if we know the angle of wall friction, angle of internal friction, using this empirical diagram, we can find out the conical Hooper angle. We can get the conical Hooper angle. So for example, let's say from the Janicki shear tester, we found out that the angle of wall friction is 20 degrees. Angle of wall friction is 20 degrees, right? And let's say, and this is found out to be 40 degrees. This is found out to be 40 degrees. Right? So we want to find out what is the maximum conical Hooper angle. We can find out from this simple empirical graph. So angle of wall friction is 20. I need to simply extend. Which line I need to select? I need to select the 40 degree line. 40 degree line is double dash. So this is the line. This is the line. So if I extend, I will get the this must be the maximum conical Hooper angle. Maximum conical Hooper angle. But of course, this is an empirical one. There must be certain amount of ideal assumptions, or while calculation there must be some errors. So Janicki suggested to take 2 to 5 degree as we need to add with whatever value we're getting, we need to add this one to 2 to 5 degrees. Usually, average value of 3 degree will be taken as a factor of safety. Whatever value you get from this graph, we will add 2 to 5. Usually, they will add 3 degrees to get the conical Hooper angle. Okay, so Janicki found out this empirical correlation, and this helps to find out the conical Hooper angle. Although this has been published 100 years ago, but this is widely used even now. It's completely valid and perfectly, excellently used. The lower the angle, always get the mass flow. If the angle is higher, then it leads to the funnel flow. Lower the angle, we'll always get the, sorry, we have to subtract whatever value we get, we need to subtract 3 degrees. Sorry, whatever angle we get, we need to subtract 3 degrees to get the mass flow. You all understood? Any question here? So the previous slide, I've explained angle of internal friction, angle of wall friction. Based on this, how to find out the conical Hooper from the Jenke's empirical correlations or empirical diagram. So I think I have covered almost all fundamentals, concepts, procedures so far. So let us go into the design procedure. Let us go into the design procedure. So whatever I explained before, I just summarized into various steps. I summarized into various steps here. So first one is we have to establish the flow function from the uniaxial compression test. That is unconfined yield strength versus compacting or consolidation stress. I'm sure all of you understood this. From that we get a line like this. This is also called, in textbook they refer, this is also called yield. Yielding, right? Yielding means flowing. Yield loci, yield locus or yield loci. Yield loci, that is flowing function. At different compacting stress, we get different unconfined yield strength. So this is called yield loci. This yield loci also can be, you can get from uniaxial compression stress. Also, you can get from the Mohr circles. Mohr circles also we can get. Right? So this is experimental one. Okay, this we need to get it from the experimental. In Mohr circles from the experimental one only. Then we need to determine angle of internal friction, phi c, and wall friction, theta c. I have showed you also today's class from the Shear Tester how to get this one and how to get this one. So these are three we get from the experiments. Then we need to determine the Hooper angle, because for the mass flow or the flowability of the particles entirely depends upon the Hooper angle and the outlet dimension. So we need to determine the Hooper angle. So just now I have showed this slide, the Jenke's empirical diagram. So we know wall friction, and we select the, sorry, here I have showed different, please notation slightly different. This is X and this is E. Sorry. This is E and this is YX. Students, I have to refer few books to make get a proper understanding and to present in a proper way. So there will be slight change in the notations, and kindly don't get confused. Okay, please don't get confused. So maybe I should write here, because in recording it will be there. Wall friction. This is internal friction. Internal. So just now I showed, based on these two measurements, how to estimate the conical Hooper angle theta c. Right? So this is directly from the empirical graph. Then we need to determine the flowability factor, FFC value, flowability factor. Again, the flowability factor, to estimate the flowability factor, Jenke has developed empirical data based on the experimental evidences. And here, so this is theta c, and this is phi w. This is wall friction angle, wall friction angle. This is conical Hooper angle. Conical Hooper angle. Conical Hooper angle. HOOPER. And here is the angle of internal friction. For 30 degrees, we have to use this chart. For 40 degrees, we have to use this chart. For 50 degrees, you have to use this chart. For 60 degrees, you have to use this chart. For in-between value, we need to do the interpolation. For in-between value, we have to do the interpolation. Okay. So, let's say the angle of internal friction is 30 degrees. You know, we have conical angle, let's say the, whatever, previous example we take, 20, previous example is 40, right? Angle of internal friction is 40, angle of wall friction is 20. So this is 20, and so I think at the time we got something around, so maybe by -3 we get this value, by -3 we get this value. So this is theta c, this is theta c, we extend here, and this is the phi w wall friction, and this fits in this line. So ff value equal to 1.5. The ff value equal to 1.5. So the flowability factor FFC is 1.5. So this way we will find out the FF value. Sorry, this way we will find out the FFC flowability factor value from this graphs. So we have 4 graphs for various internal friction angles. Then we need to determine the critical sigma c. Critical sigma c or sigma critical. Sigma critical. So we define, I already explained, we get the unconfined yield strength versus compacting stress, the flow function, and we know FFC value from the previous graph. So we draw a line from the origin with this slope. Then this is the sigma critical. So after that, we know cone Hooper angle theta c. From that, we get the h of theta using this graph. After h of theta, we estimate the outlet diameter of the Hooper. Outlet diameter of the Hooper B equal to h of theta sigma critical bulk density into G. So we got this theta and we got this B. Now we need to find out what is the Hooper diameter. We need to find out what is the Hooper diameter and what is this length. So what is this height? What is this height? We need to find out. I didn't put this one exclusively because we know if you know the mass of solids to store. Suppose if you know the mass of solids to be stored, we can calculate the volume of solids to store. How we calculate? Mass by bulk density. Mass by bulk density. This is the volume of solids needs to be stored. So this volume of solids to be stored equal to the volume of this and plus volume of this cone. V plus VC. I'm sure we all know these formulas, so we can easily calculate. So we know, since we know radius and we know this theta, obviously we can calculate this height. So we know we know this. So we can easily find out height. So this way we get diameter. Of course, we have to fix diameter to find out the height. We have to fix the diameter to find out the height. We have to fix one out of two. So H we know, we can calculate diameter, we know angle, we know B, we all know everything, right? Now this construction, the silo construction material should have certain thickness, right? Should have certain thickness. If you store large material, the thickness has to be larger. If you store less material, thickness has to be less. But what is the actual thickness value? What is the thickness of construction material? The thickness of the silo construction material. This will be estimated from the stress profile. This will be estimated from the stress profile. Okay. For time being, I will not get into stress profile. Maybe after 15 minutes, I will come to the stress profile and how to calculate the thickness from this calculations. First of all, I would like to solve few problems or one or two problems on this B and cone angle. Then we'll come to other calculations. So once you have this outlet diameter, outlet like this, the mass flow rate of the particles that can come out can also be estimated from this empirical expression. So the mass flow rate of the particles is equal to pi by 4 root 2 into bulk density into G into height of the hooper, the total height of the hooper into outlet diameter. These are the simple we explain. Then we know how much amount of particles that can come out from a hooper. So I think that gives a complete picture of a silo. So far, I have covered beginning from the class 1, when we do open storage, when we do closed storage. When we select, then when we have silos, then we have the hoopers, when we have the bins that I explained. Then we explained exclusively silo because that is only the complicated. Other two are very simple. Hooper and silo both are interrelated. Then I've explained various stresses, various conditions, various factors we need to estimate. I have covered all. Finally, I come to this silo design. The silo has diameter, height, cone angle, and diameter, and how much mass I can get, and what is the thickness of the silo material. We can also calculate. That part I haven't covered. So the part 9 will cover probably after 10 minutes. Okay, guys, do you understood the silo design? We'll solve one problem right after this. But if you have any questions so far, just let me know now. Understood? Maybe I'll ask that one. Okay. So let's solve one problem. Maybe I request all of you take a pen and paper. So far you may not need, or those who do running notes might use it. But those who can you please take pen and paper and try to just put down what is the information is given in this one. Strength is only half, huh? Only 110 or 120 out of 230 students. 60% attendance. All right. Anyway, all big guys. So I know you all know what is important, what is not important. Right. So let me read the question. The powder having an angle of internal friction of 30 degrees, an angle of wall friction, the angle of friction on SS. SS refers to stainless steel. SS refers to stainless steel is 19 degrees. A powder having this characteristic and this characteristic. First characteristic is angle of internal friction of 30 degree. Angle of wall friction is, why I say angle of wall friction? Because angle of friction on SS. SS is the stainless steel, that is the material of construction for this hooper, is 19 degree. That powder needs to be stored in a silo. That powder needs to be stored in a silo. Another property is bulk density of the powder is 1300 kg per meter cube. Bulk density of the powder is 1300 kg per meter cube. For this powder, to store this powder, they have to design the conical hooper. Conical hooper stainless steel silo. So since they haven't given amount of material, mass of material, we don't need to calculate diameter, we don't need to calculate height. Since they just only design the conical hooper stainless steel silo, they asked to calculate what is the conical hooper angle and what is the D value. Basically, they want only these two. If later they may ask if you want to store, let's say 10,000 tons of powder needs to be stored, then we can calculate diameter and we can calculate height and other factors. And we even to calculate thickness, we need this number. So, right? So we need uniaxial compression test results. So this is uniaxial compression test result. This is sigma C. Sorry, I think I written wrong. This is sigma 1. I just misplaced. This is the consolidation stress and this is the unconfined yield strength. Okay. I think by mistake I've written. So this is the sigma 1 and this is the sigma C. Okay. The first row is consolidation stress and the bottom row is unconfined yield strength. Okay. So first of all, as the design procedure I have explained, first of all, we need to plot the flow function. First of all, we need to plot the flow function, right? So what is the flow function? Unconfined yield strength. Okay, this I have taken from different books, so notations is different. Kindly don't see the symbols. Just see the what is there in y-axis. Okay, unconfined yield stress versus compacting stress, and this is sigma 1. Yeah. So I have taken this from one book, and I will upload that book today after my class. Okay, I will upload that book. So that book gives some exercise problems also, and I will solve one problem, and I'm going to there are 2 or 3 problems in this book. I don't remember exact number. All of you please practice it. All of you please practice it. And another important thing, I wanted to inform you that next week, according to the academic calendar, next week we will have the first class test. Next week we have the first class test. The class test will be conducted during the class hours only. The class test will be conducted during the class hours only. For my part means whatever I cover in these last 3 classes, I will conduct a test based on this on next Monday. Right? So test questions, all the thing I will email, okay, in detail, because I don't want to take time here. We have only 15 minutes. All the details, test, how many marks, what is the pattern, how I'm going to conduct test. I will send an email because only 120 students attended. So I wanted everybody to know. So I will email all the students about the test details. Next Monday, as per academic calendar, class test 1 needs to be conducted. So I will conduct the class test 1 in the next Monday, in the class time. So Monday class test on mechanical operation will be only from my portion. Manoj sir will conduct for his portion in his class hours, and he will announce that. So don't get confused, okay? Don't get confused. If you want, I can show you the academic calendar later if time permits, but otherwise you can also refer. If any discrepancy or anything, please let me know. So that the problem statement given that angle of internal friction is 30 degrees, angle of wall friction is 90 degree. Okay. So I think again I have written the same notations mistake here. This is the phi x. So total L cross phi x and phi 30 degrees and 90 degrees. So how can I calculate Hooper angle from this? Can anyone tell me? From these two, how will I able to calculate Hooper angle? Can anyone say? I know angle of internal flexion, angle of wall flexion. Now I want to find out the conical Hooper angle. Here I have calculated it, but how do I get this number? Can anyone suggest? Are we able to calculate from this angle of internal flexion and angle of wall flexion from that conical Hooper angle? Are we able to or not? No idea. Are you there? Or the connection disrupted? Students are able to hear my voice?
Yes, sir.
Yeah.
Yes, sir.
So how do we estimate? No idea from any students. How do you estimate conical Hooper angle from that? Those two numbers, wall flexion, internal flexion. Oh, that means you are not able to understand what I'm explaining. So just I explained before. Yeah, to determine Hooper angle, we have a empirical graph between wall friction and we have the internal friction. So internal friction value is 30 and wall friction value is 90. So this is 19, somewhere around here. And I need to take the internal friction of 30 and this is the line. So it will touch here. Yeah, if I exactly take 19, probably it comes to be 30.5. If I take exact 19, I get 30.5. So for factor of safety, we need to subtract 3 degrees first to bring into the mass flow direction. Then that will be 27.5. That will be 27.5 degrees. Do you understood, students, how to calculate this? Out of 100 plus
Yes.
students, at least one should understood.
Sir, can you please explain again? I haven't understand.
Right. So here the question they given that the powder has angle of internal friction of 30 and angle of friction on stainless steel material, that is wall friction. Angle of wall friction is 90 degree. Okay. So we know these two, 30 degree, 19 degree. Once we have this, once we know these two, we have to use this chart. We have to use this chart. We have to use this chart to find out theta c. What is theta c? This is the theta c. Theta c is the conical Hooper angle, theta c. So this is silo and this is the Hooper and this is the angle theta. Theta c. So angle of wall friction is given is 19 degree. So this is 0, 10, 20 and roughly 19 will come here. Right? If I extend this line, where to extend this line? I need to select the 30 degree line because internal friction is given to be 30. Internal friction given to be 30. So we have many lines, 1, 2, 3, 5 lines because we have five different internal friction line. So this is the 30 degree line. This is the 30 degree line. right? From the 30-degree line, we need to, this should be intersect. This needs to be intersect, right? We have to find out the points of intersection. We need to find out the point of intersection. At that point of intersection, we extend to the x-axis. We extend to the x-axis. This is the maximum conical Hooper angle. Maximum conical Hooper angle. Maximum theta c is 30.5 from the graph. But as I said before, this is, there could be certain empirical, experimental errors could be possible in reality. That's why they say we need whatever value. This is 30.5. Okay, sorry, my writing is not proper. 30.5 degrees. So this could be an idealistic mark, may not be. There could be some errors in the experimental level. To find out exact value, this has to be subtracted with 3 degree. The range is 2 to 5. The range is 2 to 5. We need to subtract to get a factor of safety value, that is 2 to 5 degree. Often they subtract 3 degree. So we get the conical Hooper angle is 27.5 degree. Do you understood now?
Yes, sir. And sir, how to find out the values in exam? Will they give us, or
Yes.
there
You
is any
don't,
other process?
yeah, you will not. We won't ask you to do any experimental measurement. We will give this value.
Okay.
Exam, there will be the question like this. I have given the question, right? Problem statement. Probably as soon as I announce the exams, everybody calm down. Huh? What can I do? Academic calendar says so, I have to follow. Otherwise, I also announced in the beginning of semester that we stick to the academic calendar. So the Hooper angle, the conical Hooper angle is 27.5 degree. Now we have to find out the FFC value. Since you don't understand Hooper angle, you might not understand the FFC also. So let me explain once again. So to estimate the FFC, we need angle of internal friction, angle of wall friction, and Hooper angle. We need all the three. To find out the flowability factor value, we need angle of internal friction value, angle of wall friction value, and Hooper angle. So, yeah, so to determine FFC value, I'll erase it. So we have three things we have three things so far problem. We have three things. One is angle of internal friction phi E is 30. And we have angle of wall friction is 19. And we have conical Hooper angle theta is 27.5. So we have three values. Okay. So as I said, for theta c 30, we need to use this graph. For phi e, angle of internal fraction 40, we use this one. In the next slide, we have 50 and 60. Since angle of internal friction is 30, we have to use this chart. So wall friction, angle of wall friction is 19. So we need to use, again, we need to get the 19. So this is the 19. And this is the theta c. This is the theta c. So theta c is 27.5. Somewhere around here, 27.5. So this is the 27.5 line. 27.5. And this is the 19. We will see where it intersects. We will see where it intersects. So it intersects on this line. And this line represents what? FF of
The
1.
FFC value.
FF is 1.8.
1.8. Yeah. Thank you. So FFC is 1.8. I got the FFC value. Sorry.
Sir, I have a doubt.
Yeah.
Sir, like we have given like sigma 1 and sigma c's graph, so can't we directly like calculate the ratio and that would be equal to FFC as the formula you have mentioned earlier?
Where did I given sigma c and sigma 1?
Sir,
Where did I give?
sir, the graph like sigma 1, sigma c flow function.
This is the flow function, but you don't know this silo conditions, right? This is the general flow function. We don't know what is exact sigma 1 we need to take.
Okay, sir.
So that's why we have to use the Janicki's empirical charts to find out the FFC value based on the internal friction and the wall friction values. Okay?
Okay, sir.
Yeah, thanks. So once you know FFC value, we draw a line from origin with a slope of 1 over FFC. With a slope of 1 over FFC. That basically touches here. This is the flow function, powder flow function, and this is the line to intersect, and this is the critical, sigma critical is 0.83. So critical stress is 0.83 kilonewton, forgot to write units, sorry, kilonewton per meter square. So I found out Hooper angle, FFC, and the critical stress. And H of theta. H of theta from the Hooper angle, conical Hooper angle. This is the H of theta. This is the conical Hooper angle. So this is 27.5. Why? So this is the 27.5. Right? 27.5 we get a number, and this is something around 2.4, I guess. 2.46. H of theta is 2.46. So once I know H of theta and all these things, I can use this formula to calculate outlet diameter of the Hooper. Or diameter, this is the outlet diameter of the Hooper, B. So B equal to H of theta, and this is sigma critical bulk density and G value. I have to make sure same unit consistency, so kilo units is converted to meters, and this is the 0.16 meters. 0.16 meters. If I know if the given mass of solids to store, we can convert into volume of solids by dividing with bulk density. Then we can calculate diameter and height. So this way, to get a mass flow in a silo that is easily uniform flow the particles in silo, we have to follow this procedure. If you don't follow the procedure, you will get flow obstructions. Once we have flow obstructions, it can lead to the damage, silo damage, or you will not end up any particles to come out from the silo. Okay? Probably from my last responses, I could understand that some of you are not able to understand. But I think this is very, very simple procedure. So I request allocate some time to listen to my recorded lectures. There's only 3 lectures, right? So far only this is 3rd lecture. So it's not long, it's not at all rocket science. Genuinely, if you have any questions, you can message me using MS Teams chat option, or you can ask during the class. I will be very happy to explain, okay? But my only request is, after explaining so much, if few students also could not understand, then I think there must be some mistake somewhere. If you think mistake from my side, I'm very, very welcome to take your suggestion and put in a way you all can understand. If you didn't pay attention, or if you don't have time to refer my notes or previous slides, please do refer, okay? That will be helpful. Without silo, there is no process industry. If you have any industry, there will be silo, because almost all industries has to store solids, has to transport solids. So silo will be there. So this is very simple. Okay, you may say at the end I brought it to very simple design procedure charts. But why do you explain? Because I want you to understand so many factors. In a class like this, in 6 hours, we won't be able to cover so many things. You know, Silo has further add-ons to understand all these background details helpful. So that's why I gave a flavor of a particle mechanics, flavor of various fundamental studies to understand concepts more stronger. So I have given another example, another problem here. I want all of you to practice later at your home. Okay. If you have any doubts, you can always message me. I will be happy to explain. And I will be asking questions on these in the class test coming on the next Monday. Not only this, all whatever I cover in the last 6 hours, I will ask questions based on that. It is actually good for you. You know, we are conducting tests in between, so that you don't have to read whole thing at a time. Part by part you can read. So whatever I cover here, I will give in this test. Whatever I cover in next block, I will give in that one. That way, I will make your life. We are making your life very simple. But unfortunately, you have to study regularly. That is the thing. But I'm sure after giving the JEE exam, you don't like to do that. But that is the life. So I wanted all of you practice this. I will also upload a book in this MS Teams folder, and on this, and you all read. You will understand, or you can use exercise problems to practice further. Any questions, students? Any questions you have so far? Then I'm moving on to the next part. That is, to calculate thickness, we need to estimate the stress profile. So I'm going to the stress profile explanation. Before that, if you have any questions, please ask me. If you have any questions.
Sir, can you just once again explain why we didn't calculate FCC using the formula sigma 1 by sigma c?
Right. So we have only flow function. Okay. We have only flow function. If this flow function for various sigma 1, we have the various sigma c values. Okay. Now we wanted to find out the sigma value that is applicable for the silo conditions what we are interested. So we have the silo, and we can only measure angle of internal friction by the angle of wall friction by W, right? In a large silo which can store almost 10,000 tons, for example, or 1,000 tons, whatever. The sigma 1 is compacting stress. Sigma 1 is the compacting stress. Compaction takes place from the top to bottom, right? As the load goes on, the compaction takes place. More and more amount of compaction is as you leave out. As you leave for longer, more and more amount of compaction takes place. The compaction levels varies from the point to point. The compaction levels also varies from the point to point. So it is very difficult to find out what sigma 1 we need to take. Rather, Janicki has given another way to find out FFC. If you know exact, let's say if we have any small cup of powder, let's say you have the small cup of powder and you have applied the known amount of compaction, you can find out sigma 1, and from the sigma 1 you can find out the sigma c, then you can find out the ratio, whatever K. But in a silo, this is difficult to find out because that varies from the level to level, height to height. It depends on other factors. So it's difficult to find out all those. Rather, it's very easy to find out these two because this way doesn't vary. These two doesn't vary. This is because they're the powder flow properties. So Janicki has developed a correlations based on the powder flow properties to estimate the FFC. Hence, we are using this. If you know sigma 1, if we say I have uniform conditions, I can easily estimate sigma 1, yeah, you're welcome to just take the sigma c versus sigma 1 ratio as a FFC. You understood? Now at least?
Yes, sir. Yes, sir. Thank you.
No, you understood, right? Genuinely?
Yes, sir. I
Okay.
understood.
Not to that, I just to say, okay, if you understood, I will be very happy.
Yes, sir. It is clear now.
Yeah, thank you. Any other students, any questions? Don't hesitate that I have already asked question. If you don't understand, you can ask again. My aim is that you should understand, right? Rather than just covering the topics, you should understand because you guys has to learn. I'm teaching for you to understand, not to just to complete the syllabus. Okay, so I'll move on to the next one, that is stress profile in silos. Okay. Whenever we want to derive any profile, either in reactor or fluid flow, anything, how do we derive profiles? Let's say this is the silo, and I want to derive the variation of stress. I want to derive the variation of stress along, let's say this is the whatever height. I want to see the variation of stress. How do I find out this profile? What is the procedure we use in typical chemical engineering? Anyone remember? Anyone knows? Whenever we have a large body and we wanted to find out a profile of variation of one parameter with respect to other one, how do we find out? We always take, let's say, V amount of vertical load is applied, sigma V naught amount of vertical load is applied onto this silo. Whenever we wanted to find out stress profile means what? How stress is varying with respect to one parameter. Here we wanted to find with respect to the height. Here we want to find out with respect to the height. We want to find out the variation of one with respect to other one. Instead of whenever we want to find out variation in a large one, what we take? We take a small element. We take a small element, and we find out the why we take the small element. Within the small element, we assume that within the small element we can assume that the variation is linear or very minimal, because that is a very small element. Then we derive an expression, then we integrate to the whole body. Then we get a differential equation, then we integrate to get the overall system. Do you remember now what is the procedure we use, or have you come across such procedure earlier? Whenever we want to find out the variation of one parameter, we will take a small element in a large body. Then we do the force balance, whatever based on the mole balance, whatever required based on that, we do the balance. Then we get the expression for the small element. Then we integrate to the whole system. So here we wanted to find out the stress profile, how the stress is varying with respect to the height we wanted to find out. So we take a silo, and here we have the vertical load sigma V naught, and we take Z is 0, that is the top of the silo. At a Z distance, I have considered the small element. I have considered the small element. Since we have wanted to find out the stress profile, stress comes from the force balance, because force per area equal to stress, it comes from the force balance. So these are the forces. These are the various forces acts on the small element. These are the various forces acts on the small element. So this is a small element, and let's say at Z, okay, at Z, amount of force acting, that is normal force, normal stress into area, that is normal force, right? Normal force equal to normal stress into area. Since we want to derive the stress profile, I have expressed in terms of stress into area. at z plus delta z, at z plus delta z, and we have the variation of the delta V or dV, the delta V amount of stress being increased or reduced, whatever, that is the delta V into area, right? And this is the horizontal stress. Because of the horizontal stress, we have the resistance offered by this small element, that is shear stress. That is the shear stress. Shear stress acts in this direction, so we need to take the element area, that is A. So this is the top view, and this is the side view. So for the normal stress, we take this area, cross-sectional area, that is pi by 4 d square. For shear stress, we take this area, that is u into dz, that is pi dl or pi dl, right? So here u is pi d. So that's what the shear stress. And for this element, gravitational force acts. Gravitational force mg. Gravitational force is mg. M, how do you calculate M? That is mass of solids in this element. M is basically mass of solids in this element. Mass can be written as volume of the element into bulk density, because mass by volume, bulk density is mass by volume. Volume gets cancelled, we get the mass. So volume of element is nothing but what? Area into dz. Area into dz. So we get rho, bulk density, into A into dz. This is M and mg. So this way I got the gravitational force expression. So we have all the forces: normal force, shear force, and the gravitational force. There are the three forces action here: normal force, shear force, gravitational force. There are three forces acts here. So if I write the force balance, I get this expression. At z is A into sigma V plus gravitational force. Downward direction, two force acts: the top vertical stress and the gravitational force. Sorry, top normal force and gravitational force act in the downward direction. Shear force acts in the upward direction. That is this shear force, tau W into U into dz. Then we have upward force, upward normal force acts, and this one. Right? So these are the total force balance. Simple, three force acts: normal force, shear force, and the gravitational force. So if these get cancelled, because A into sigma V and A into sigma V get cancelled. Then we can rearrange, because we have A into d sigma V, A into d sigma V here, and here nothing is there. So dz comes, and dz get cancelled. We have u by A. So finally we get this expression after simplification. Hope you understanding. G into rho B into A into dz equal to A into d of sigma V plus tau W into U into dz. So here the A into dz brought here. So we will have A into dz. So here we get A into right plus this to get cancelled U by A equal to G into rho V. So this term brought this side, so that's why you will have the sorry, not this term. This term brought this side, so you have d of rho v by dz. If we turn this, we will get this way. Some doubt?
Sir, if we are A, then
Sorry?
that A d sigma v by dz will not be there. The A with A multiplied by d sigma v.
Sorry, student, I could not understand. Can you repeat once again?
No, sir. In that equation, you had already divided by A, so you had written again A along with d sigma v by dz.
Oh, okay, okay. Sorry. Thank you. Yeah, thank you. So the fairly simple one, just know the way I have written. And we know K equal to horizontal stress by the vertical stress, lateral stress ratio. We can assume, we assume K is constant, but in reality K might vary because the compact stress or sigma h vary from height, distance to like the level. We know another relation, that is angle of wall friction. Angle of wall friction equal to tau W by sigma h. I have explained today also how to find out the angle of wall friction. So tan, sorry, notations are varying. I'm really sorry, but kindly keep that in mind. This is actually, instead of pi W, I written pi x here. Tau W by horizontal stress. So here, what I wanted to do is just want to eliminate this one into the known terms. The tau W, I want to eliminate into the known terms. How do you eliminate? Tau W equal to horizontal stress into tan pi x, right? And what is this? This equal to K into sigma V. Yeah, so tau W equal to K into sigma V into tan angle of wall friction. Because angle of wall friction can be measured, K can be measured, and sigma V is known. That is the load acting from the top, or it is a variable. That is the variable. So I've just substituted this here. In this formula, I have substituted this. In this formula, I have just substituted this. Right? So you get this. If you substitute this one, tau W as this one, you get this one. So obviously, we wanted to find out the overall stress profile. So we wanted to integrate 0 to Z. So here we just initially want to find out only for top section. Okay, this derivation only up to this part, right? So Z is here, 0 to Z, 0 to Z. So 0 to whatever H or Z, whatever Z, maximum or Z1 is from initial vertical stress to the vertical stress at this Z value. We get this expression, and I'm sure all of you very good in this integration part. So this will be the final expression. This will be the final expression. I think we should all try later how to get this one. So this is the expression for stress profile. This is the expression for stress profile. This is also derivation from the Janicki only. This is also derivation from the Janicki only. Janicki is a person, a scientist who extensively worked. Sorry, Jensen, not Janicki. This is the expression from Jensen. I'm sorry, just misly mentioned, wrongly mentioned. Jensen's expression. Janicki and Jensen, these are the two important people, worked extensively on the particle kinetics, particle mechanics, and the silo design and everything. So, same expression, whatever I showed in the previous slide, I just rewritten here. So here is Z is the variable that varies from 0 to Z max, and this is the height, critical height, we can say. Then it becomes e to the power of minus Z to the power of LC. Z to the power of LC. So let's say Z is very big value. If the silo height is very big, this silo height is very big, 0 to Z, we say. Right? It's very big. If you take the Z as infinite, and we know this will come as u to the power of this expression will be 1 over e to the power of Z by LC, right? Z by LC. This expression will become like this. When Z tends to infinite, what will happen? This is infinite. 1 over infinite is 0. So whole this term gets cancelled. Whole this term becomes 0. So you will have only this term. So that is what represent here. So for very one important observation we wanted to emphasize here is that for very higher heights, for very tall silos, the stress at the bottom of the silo, okay? Stress at the bottom of silo doesn't depend upon sigma V naught, initial stress. There is no initial stress value. Doesn't depend upon, okay? No dependency on this one. It is just depends upon powder properties, K, phi x, and the Hooper diameter, Hooper area, and bulk density only. So, what is called very significantly tall? What is called significantly tall? When we say significantly tall, if Z by LC, if the Z by LC ratio, okay, if the Z by LC ratio becomes very high value, if the Z by LC become very high value, then we can say Z tends to infinite. When the Z by LC become very high value, if L by D is 4, greater than 4, if L by D is greater than 4, then we can say this value will become very high, and then we will get this expression. So one important conclusion people have drawn that this is D, okay, and this is L. This is called aspect ratio. Whenever you have a cylinder, L by D ratio is called aspect ratio. If L by D is greater than 4, stress acts at the bottom of the silo. Stress acts at the bottom of the silo is independent of the initial vertical load. Or there is no load term at all. There is no load term. It is only powder flow parameters. Yeah. Sorry, fully messy. I'll just erase these things. Right. So hope you pay attention and understand whatever I'm trying to explain. So that is the ultimate, this is called ultimate vertical stress. So vertical stress by ultimate vertical stress, same, this expression rewritten in this form. This expression rewritten in this form. Right? How we got 4 by d? We know u equal to pi d, u equal to pi d, and a is pi by 4d square, right? I am talking about u by a. Here I am talking about u by a. U by a is pi d by pi by 4 d square. So you get 4 by d. U by a is nothing but 4 by d. This is 4 by d, right? 4 by d. So if you plot this, if you use this expression, either this one or that one, if you plot Z versus vertical stress, if it is, this is for liquid. Suppose you have a liquid. If you store a liquid here, you get hydrostatic pressure. The stress is coming from the hydrostatic pressure. That is P equal to rho g H. Probably you all studied already in fluid mechanics course, fluid static, hydrostatic pressure to this one. But for solids, entirely different. And for solids, this is entirely different. So it comes like this form. And after certain height, it will reach some asymptotic value, means a constant value. After certain height, that will reach an asymptotic value. What is that height? If L by D, length by diameter is greater than 4, people found out that it reaches the asymptote, a constant value. Doesn't vary at all after that. The vertical stress doesn't vary at all after that. If vertical stress is 0, let's say only gravitational force acts, there is no additional vertical stress, and this is the formula. This is the formula for vertical stress. If there is no external vertical stress, it's only gravitational force. If it only acts by the gravity, this is the vertical stress. Yeah, this is the plot how the stress profile varies. You can easily understand from this. Just non-dimensional, rho v, sigma v by sigma v infinite in the y-axis, and z by d in the u by a is d, right? So z by d, if you plot, you get this graph. So I want all of you to calculate this later. Very, very simple and straightforward. Consider the wall of cylindrical silo made of a material that can bear the maximum stress up to 4.4 kilopascals. 4.4 kilopascals. Okay. Assume that only possible source of damage at the wall is horizontal stress except by the bulk solids on the wall. Yeah. So if there is no surcharge stress, that is additional external stress, calculate the maximum height allowed for silo to avoid any damage. Calculate the maximum height to avoid the damage. So basically, this we have to take as 4.4. We have to take this as 4.4. This I take 4.4, and you need to calculate the Z value. You need to calculate the Z value. Yeah. Right. So I'm sure all of you will calculate, and probably I'll upload the solution. You all can try and upload the solution by tomorrow. You all can cross check. So this is the top part of silo. We have just derived the stress profile. One important observation that when you fill the material in the stress profile, below this line, that is below this line, whenever the particles are filled, up to this portion, right? Up to this portion, most of the load is diffuses in this direction, vertical direction. Very less load on the walls. Very less loads on the walls. But when it comes to the Hooper, since this slant line, the most of the load distributes towards the wall material. and the net amount of vertical stress decreases. Net amount of vertical stress tend to decrease. That's what people have observed experimentally, right? So the vertical stress decreases, and if it crosses zero, of course, this zero refers to the 0 point. That this refers to the 0 point. So we'll have always, we need to have a certain amount of stress for the minimization of arc formation. So that is why the vertical stress is decreases down. The derivation similar to the previous derivation I have given after a few slides. I don't want to take time to explain because that is exactly similar to the previous one. Please go through that. All of you, please go through that. So very quick. So here, one scientist kept the pressure sensors at different locations. One scientist kept the pressure sensors at different locations, starting from bottom A, B, C, and D. Now here, there are two things. Stress profile varying during filling and emptying. So they have filled up to this point. Up to the filling ends at the 31 minutes, right? So during filling, you can see that the stress profile increasing and reach an asymptote value. Just now we have seen. While discharge, there is sudden abrupt rise in the stress profile. While discharge, there is sudden abrupt increase in the stress profile. Why this sudden abrupt discharge is taking place? This is the same thing I have explained here. This is during the discharge. At some point of time, you will see there's a peak, increase and decrease, and the stress profile varies like this. The stress profile varies like this. Won't be like a perfect smooth line what you have shown earlier. It's not like perfect smooth line like here, but there is a variation, random variation. But Jensen has approximated to be a smooth variation, and that is why we get the line. But we are interested only maximum. We are interested only the maximum stress, because if we can accommodate maximum stress, we can accommodate the lower stresses also. That's why we can use the Jensen's request to find out the maximum yield stress. The last point, which I explained here, this is the during the emptying, the stress field during the emptying, right? As I said, below the horizontal part during the Hooper, most of the load distributes towards the wall, but in this top section, the load distributes in the vertical direction, less loads on the wall. As soon as you start emptying, what happens? The K or the sigma C versus not K, FFC sigma C versus sigma 1. The flow bill entirely depends upon this, right? As you started emptying, right? As you started emptying, the compactness will not change. Compactness initially we get compact, and the critical stress value is fixed, right? The stress value fixed. But as is emptying, this value reduces. The compact is loosened. The compacting is loosened. So the FFC value greatly increases. Because of the flow also enhances. The flow also enhances as emptying. And people have observed that the stress profile varies this way. Because of this changing variation, initially the stress profile is like this, but during emptying, the stress profile became like this. Because of this variation, you will see this abrupt increase in the pressure. So, if the abrupt increase in pressure is significantly high, you will see a buckling effect. People have observed that suddenly the silo got broken or silo got just simply compressed. This is called the buckling effect. That is why when you do the stress calculations, we should not use any stress value. Rather, we have to use the maximum stress value. We have to use the maximum stress value. That maximum stress value, we can almost take it as infinite height, this value. We can take this value. From this stress, we can calculate the thickness. From this stress, we can calculate the thickness. So that is what I was trying to mention here. Yes, thickness calculates from the construction. Yes, please.
I was asking about, like, although it is impractical, but if we were to maintain the compactness, like at each and every, like we release the flow by a little amount and maintain compactness at each step, then we would get the curve that the Janssen equation predicts, right? Like, although it does not suit the practical experimental flow curve we are getting.
Actually, I could not follow your question. Can you say once again?
Sir, the curve predicted by the Janssen equation,
Yes.
like it is very idealistic in the sense that it requires the same compactness at all times, if I'm getting it right. The compact.
We have assumed, right? We have assumed uniform compactness in there. Where do we assume the uniform compactness everywhere?
Means like throughout the flow, the compactness remains the same. Although it practically it is not happening.
No. We haven't assumed compactness varying. We have a compactness varying. That's why vertical stress is varying. We are not assuming that. Janssen equation predicts the ultimate or the highest vertical strength. Why we need to use highest vertical strength? I'm just trying to explain using these principles to apply the buckling effect.
Okay, sir.
So just given a small question, diameter, height, probably you all can do it. And this is the derivation which I use for the Hooper profile, stress profile in Hooper. Just simple force balance. I think all of you, if you understood the previous one, you will be able to understand this also. So with this, probably my ending was not smooth. So with this, I will try to explain the design procedure in detail. Okay, so these are the steps of design, and so while solving problem 2, I will try to put all those steps. So thickness calculation, and for the maximum stress, ultimate stress value comes from the stress profile, we will use to find out the thickness calculation. So we could find out diameter, height, thickness, angle, everything, and that concludes the silo design. Okay, students, thank you so much. And if you have any, and I think it's already crossed the time, so I'm sorry for that. Just I wanted to finish the topic. Don't want to postpone to the next class. So I will take up if you have any questions.